Namaskar, good morning. My name is Panindra Kumar. Ours is a startup company basically concentrating on research and training. This is the first video, and today I will be covering about earthing of AC substation. We will be using the standard IEEE 80 to do the earthing of AC substation. So basically, I will be guiding on how to design the earth mat of a AC substation. As we go in the topic today, I will explain what all is covered, what is not covered, and also we will have two videos. One video will tell about the basic of the design, and in the second video I will take some typical examples of a 220 kV switchyard and talk about its design. Now in this topic, HVDC substation is not covered. Then the GIS substation is not covered. Then the earthing of industrial system or the commercial power system, that is not covered. Then earthing of generators. Generator neutral earthing is not covered in this. And HVDC, GIS, industrial, generator, neutral. I think these are the main things. And yeah, earthing related to the refinery, which is for protection against static charge, that is not covered. And I think these are the main things which we will not be covering. And also some special earthing related to electronic earthing and earthing of communication system, then earthing done for lightning protection. Now these are not covered. So this will be covered in separate topics. Now let me come back to earthing of AC substation by IEEE 80. What do we mean by earthing? The word is very clear, earthing. So any object inside a AC substation, I will not use the word AC substation again and again. I will only be using the word substation, and when I say substation, it is AC substation. Inside a substation, there may be some electric equipment. Now that equipment will be standing on some foundation. Good. So it is already connected to the earth. Then what are we talking about earthing? We connect one more metal strip to one more metal grid below the ground. Basically what we are doing is the metal above the ground is connected to the metal below the ground with the help of one more metal strip. So metal to metal via a metal. Now this metal, if you see any electric equipment is made of three things: metal, non-metal, metal. The first metal is this first metal is the conducting metal, which carries the power or the energy. The last metal is the outer enclosure, the body, which gives the protection, mechanical strength. Now, between these two, there is a non-metal, that is insulation, which prevents the flow of current from the conducting metal to the non-conducting metal. So what we do is we connect this non-conducting metal to the earth current. That is earthing. That's all. Now, why do we do this? The reason is when energy flows in form of electric current. Energy flows from one place to the other place. What happens when energy flows from one place to the another place? Under normal circumstance, there is absolutely no problem. The energy keeps flowing. Now, during a fault, what happens? There is a failure or the rupture of this insulation. So, when there is a rupture of this insulation, there is a fault. And what happens during a fault? The current flows from the conductor to the outer metallic surface, and this fault current is huge current. We have to give a safe path for this current to go to the earth. So we provide this earth strip. Now later on as we go, I will explain about the sizing of this earth strip. The sizing of this strip depends on the amount of fault current. Now when there is a fault, the fault current goes to the earth current. So number one, we need to provide a path, and that path has to be safe path. Now what do we mean by providing safe path? So let's say, in a substation, people are moving here and there, and people cannot see a fault, right? Fault current cannot be seen. So let's say somebody is standing nearby, and if he has touched this, he is doing some work. He is touching the outer body, because normally outer body is safe. You can touch it, there is no problem. Let's say he is doing some work, he is touching. So when there is a fault here, it may so happen that the fault current may flow through this body. So when I say safe path, this safety is related to this person. There are two paths, one is this path, one is this path. I don't want the fault current to flow in this path, I want it to flow in this path. So this is the safe path. So it flows in a path where it does not affect any human life. Now, later on I will explain some concept called touch and step potential. Even if a person is touching, he should not get electrocuted. As we go further, I will explain about that. So I will explain about that. Number 2, I will explain about sizing of this grid. Number 3, I will explain about how this earthing grid is sized. What should be the depth of burial, how to determine then I'll explain some concept called ground potential rise. So this I will do as we go further. So one is, I told what is earthing. So I've explained what is earthing. Then second thing, why earthing is required. I've explained this already. So the next is I explained, briefly I've explained what is fault. Now, how to calculate the fault current as we go further, I'll tell briefly about how to calculate the fault current. Okay, what is earthing? Okay, now let me tell about something called this shock. See what happens when a person touches this. When there is a fault current flowing through this strip, the potential of this rises. Normally this is at zero potential. But But when there is a fault, as the fault current flows to the earth grid, the potential of this outer metal surface rises. And when that potential rises, the person who is touching, he gets a shock. This is related to a term called GPR, which will be explained later. Now, when a person is touching any metallic object in a substation, normally there is no problem. But during a fault condition, what happens? The potential of that object rises and he will receive a shock. That is, what happens? There is a potential difference between his hand and his foot. So you know that current is nothing but voltage divided by resistor. So the voltage difference between his hand and foot divided by the resistance of his body will give rise to a current called body current. Now when this current flows through the body of a person, depending on the magnitude, different things will occur. I will explain about that. For example, see, when the body current is very less, let's say 1 milliamps, the person will only feel, he will only feel some small sensation. When the body current is up around 10 milliamps, maybe 6, maybe 15, something around 10 milliamps, he will feel pain and maybe he cannot lift his hand. Maybe the person cannot lift his hand. So the hand, if somebody is touching like this, so they cannot lift the hand because their nervous, I think it will affect the signals of the nerve. So the person's hand is like this. Maybe due to gravity it may fall. Now when the fault current is around 100 milliamps, maybe 160 milliamps or 160 milliamps or 150, something close nearby 100 milliamps, it is dangerous because this current passes to the person's heart. Something called ventricular fibrillation will occur. That is, our heart, it keeps doing its action in a particular rhythm and it keeps getting a electric signal from the brain. So when this current flows, the heart's rhythm gets affected and heart stops and the person dies. Basically, this current leads to fatality. So when we design an earthing system, our objective is to protect a person and we have to prevent the body current. We have to prevent the body current below these 100 milliamps. We cannot protect a person from 1 milliamps or 10 milliamps. That will become a very conservative design. So our objective is to prevent this 100 milliamps or 160 milliamps or 150 milliamps from flowing into the person, human body. Now how this current has come, 100 milliamp, a lot of research has been done. You can refer the IEEE publication. So several research carried out, they have determined this current. Okay, so I have told about the body current. Now, then I'll tell about this resistance. Now, when a person is standing in a substation, let us say there is some equipment like the isolator. Isolator, at the bottom of the isolator it will be a metallic structure. Let's say a person is standing here. When a person is standing on the ground, there is a resistance between his foot to the ground. So that is called foot resistance. Now if you see, the fault current flows like this, right? Now if we increase this resistance of offered along the fault path, we can reduce the body current. So later on during the design, you will see how by increasing this resistor, we are reducing the fault current. Then next, regarding this voltage, what is this voltage? When a person touches an object, the voltage between his hand and foot, that is called, this voltage, we call it as touch voltage. IEEE is all about this touch and step potential, and this voltage is called the step voltage. So fault can flow in three paths. One is from the hand to the foot, that is the first path. Then the second path is from the foot like this to the foot. The third path, if the person is touching both the hand, that is the third. But we don't analyze this third scenario because it is very seldom. So we analyze the first one and the second one. So this is called touch voltage, this is called step voltage. So basically what we have to do is, we have to determine now what is the step and touch voltage a person can tolerate. First is we have to determine the tolerable limits. Second thing, we have to determine what is the voltage that can occur in a substation. So these are the two things we have to do in the design. So in substation design, okay, I will rub this. Substation design, there are three things. One is we have to do the sizing of the earth grid. Number two, we have to determine the tolerable step and touch potential, and then we have to determine the voltage, the same step and voltage which will occur in our substation. So I think if we do these three things, that's about the design. How do we do the sizing of earth grid? First, we have to determine the fault current. Determination of the fault current is a separate topic that will not be covered here, but I'll tell you in very brief. Suppose you have any system suppose you want to find the fault current at any particular bus. You represent the entire system and write down the per unit reactance. Then you can determine the fault current. Later on, during the determination of step and touch potential, I will take one typical case, a typical 220 kV switchyard, and show how the fault level is determined. For sizing of the earth grid, let us take the design fault current. Whereas for touch and step potential, we will be taking the reduced fault current. Why we are doing like that, I will explain. Now, normally a 220 kV substation fault level will be around 40 kV. So if you go to any of the planning documents, you will get this fault current. So I have taken the transmission planning criteria by CA, and as per that 220 kV fault is 31.5 kA or 40 kA. So I will take 40 kA for 1 second. When you take 40 kA, the size of a conductor, there is a formula. Utilize the formula, you can determine the size. I will not stress more, I will not explain the formulas too much because these are straightforward formulas. You understand the concept, then everything is clear. As far as the equations and formulas are concerned, all you need to do is just refer them. You should know how to use them. The main thing is the units, because in all these formulas, you should know what unit to use, whether it is in mm or inch. So that's it. Now this fault, this cross section of a conductor, there are some the different constants to be used in this formula. See, if the conductor is copper, the constant is different. If the conductor is aluminium, it is different. If it is galvanized iron, it is different. For this protective conductor, the one which we are for the earth grid, and the link which is connecting the electrical equipment to the earth grid, these conductors can be either copper or aluminium or galvanized iron or galvanized steel. So the choice of this conductor, it again depends. Geography to geography, country to country, client to client, it changes. But one thing you have to remember, when you are using a cathodic protection, you cannot go for copper. So the best preferable one is galvanized steel. And when we are using this galvanized iron or galvanized steel, you have to size the conductor taking some 30% margin or some margin which is based on the corrosion. Because of corrosion, the size of the conductor reduces with time. So I will show all three examples. For a 40 kA for 1 second, done sizing for all three conductors. So I will show all three of them. The sizing of our grid is done using this formula. In this formula, I is the current in kiloamps. Let's take the design fault current, for example 40 kA. T cap is the thermal capacity of the conductor. K naught is a constant, alpha R is a constant, they depend on the material. Rho R is the resistivity of the conductor, that is also a constant. TA is the ambient temperature, we have taken it as 20 degrees Celsius. Tm is the maximum temperature for which the conductor can sustain, and Tc is the it is the time for which the fault exists. It depends on the tripping time of the breaker, but we will consider it as 1 second. Now this formula is like this. After you substitute the value for copper, annealed soft drawn copper conductor, where T cap is 3.42 and the maximum temperature is 1083 degrees Celsius, and the constant K naught is 234, and Tc is 1 second, alpha r is 0.00393, and rho r is 1.72. Now, allowing the copper to operate till 1083 temperature, 1083 degrees Celsius, is not recommended, because at that temperature the copper loses not only the copper will undergo fusing, and it also loses its mechanical strength. So let us restrict the temperature of the copper to a value where it loses its mechanical strength. That is, we will restrict the temperature to 250 degrees Celsius. So then the formula for calculating the size of the conductor is as shown here. For galvanized iron, the formula is as given below. The thermal capacity is 3.93, alpha r is 0.00320, rho r resistivity is 20, K naught is 293, the maximum temperature is 419, and ambient is 20. So let us substitute this formula. We can get the size of the galvanized iron